Today we're looking at the history of atomic theory. This is the short version of the presentation. Keep in mind as I go through this that atoms are so incredibly small that we cannot, nor have we ever been able to actually see what's inside the atom. All of our models of the atom are based on mathematical predictions and experiments, not what's seen or can be seen. We start our history with the ancient Greek philosophers Democritus and Aristotle. Democritus, who lived roughly 400 BC, was the first person to come up with the idea that atoms existed. He basically said, imagine a piece of gold, cut it in half. Take each half, cut it in half. Take each half, cut it in half, and keep doing this over and over and over again. He believed eventually you would reach a smallest piece of gold that could exist. That smallest piece he called atomos, which just meant indivisible. That's where the idea of atoms comes from. Democritus believed that everything was made up of these tiny particles that could not be separated. The other Greek philosopher, Aristotle, had a slightly different opinion. Aristotle believed that matter was continuous. In other words, if you keep cutting it in half, you can keep doing this over and over and over again, and at no point would you ever reach the smallest piece of matter that could exist. He also believed that matter was made up of 4 elements: earth, wind, fire, and water, and these elements could be combined in different ways to create all of the substances we know of. His idea really took off because it's a cool idea to think that if you change the balance of earth, wind, and fire, or water in a substance, you change what it's made of. Imagine taking a piece of lead and turning it into gold just by blowing on it and lighting it on fire. So his idea stuck around for several hundred, actually over 1,000 years, and then we get to the more modern era. The modern era basically started in the late 1700s with the invention of the chemical balance. Very simple invention, but it allowed scientists to compare masses of different substances. This led Antoine Lavoisier to come up with the law of conservation of mass. Now, he was a French nobleman killed in the French Revolution, but he came up with the idea that mass cannot be created or destroyed during any process, any physical or chemical process, but mass can change form. The next scientist, John Dalton, proposed the atomic theory of matter. Basically, using the balance, he was the first person to scientifically prove atoms exist. He also came up with the billiard ball model of the atom, which is atoms are basically small solid particles, and everything is made up of those particles. In fact, there's 5 points to his atomic theory. Here they are. The first one, all substances are made up of tiny individual particles called atoms. Atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ. Atoms cannot be subdivided, created, or destroyed, and atoms of different elements can combine in simple whole number ratios to form different compounds. And finally, during a reaction, atoms are separated, combined, rearranged, and reattached. Now, his idea is not 100% perfect. A lot of theories change over time, and there are 2 major changes to his theory. The first one, he believed that atoms of an identical element would be exactly identical. Turns out they're not. We now say that atoms of an element have a unique characteristic mass and unique properties. The reason why is every element exists in slightly different forms called isotopes. For example, take hydrogen. Hydrogen exists in 3 isotopes. All 3 of them have 1 proton, but the numbers of neutrons in them can vary. Some have no neutrons, some have 1 neutron, and then very few of them will have up to 2 neutrons. Every single element that exists is a blend of slightly different atoms that have the same number of protons, and the same basic properties, just slightly different numbers of neutrons and therefore different weights. So, if we look at carbon as an example, we see 3 different forms of carbon: carbon-12, carbon-13, and carbon-14. They all have 6 protons, but the number of neutrons in them can change. Now, point blank, carbon-12 is the most common in the universe. It's almost 99% of all carbon atoms are in that form. The other 2 are very rare. But because every sample of carbon has all three of these different forms in it, if you take an average mass for the atoms in any sample of carbon, they're not going to come up to 12, which is the mass of carbon 12. They're going to come up to 12.011. Now, why this number? Well, this number is very close to the most common form of carbon, but this little bit here at the end that it's off is because of carbon 13 and carbon 14, just pulling the average up a little bit. We say that this is a weighted average, meaning the atom that has the most effect on that average is the one that's the most common. Now, the other part of Dalton's theory that changed is the idea that atoms cannot be created, subdivided, or destroyed. That too is not true because we discovered nuclear reactions. So we just say that atoms cannot be subdivided, created, or destroyed during ordinary chemical or physical processes, and we temporarily sidestep the nuclear reaction issue. Now, there are three laws that are explained in points 4 and 5 of Dalton's atomic theory. The three laws: the law of conservation of mass, which again says you cannot create or destroy mass or matter. It simply changes form. In other words, the atoms become rearranged. They're never created or destroyed. The other two laws, the law of definite composition and the law of definite proportions. The law of definite composition basically tells us that every compound is exactly the same in the number of elements and the proportion of those elements, regardless of where you get it from. For example, water always has a 2-to-1 ratio of hydrogen to oxygen. Glucose always has this ratio of 1 to 2 to 1 of carbon to hydrogen to oxygen. So the law of definite composition says that a compound will always have the exact same elements in the same proportions. But the law of multiple proportions says that you could have different compounds made up of the same elements. They will be in different amounts. For example, water is a 2-to-1 ratio of elements. Hydrogen peroxide is a 1-to-1 ratio of elements. Water is H2O, hydrogen peroxide is H2O2. Now, it may not seem like a big deal, that one oxygen atom, but the difference between them, water, you have a very safe, necessary compound. Add that extra oxygen to it, you get hydrogen peroxide, which is corrosive and deadly. So the law of multiple proportions tells us that if you change the proportions of the elements, even if they're the same elements in different proportions, it changes the behavior and all of the properties of that compound. So we move a little bit further along into the modern era, into the late 1800s. We'll be studying the three parts of the atoms here: protons, neutrons, and electrons, how they were discovered, and the arrangement of those subatomic particles. We begin not talking about the atom actually, but with electricity. In the late 1800s, lots of scientists were studying electricity, and they discovered that electrical charge was the result of positives and negatives that interacted with one another. They didn't know what those positives or negatives were, but they knew that like charges would repel one another. In other words, two negatives or two positives would repel. Unlike charges would attract one another. Positives and negatives attract. J.J. Thomson in the late 1800s was studying cathode ray tubes. These were the forerunner of what modern TVs were made out of, or I should say not so modern TVs. These are the tube TVs that were very common up till about 15 years ago. His cathode ray tube experiments showed him that electrons exist. Now, the short explanation of the experiment is this. This is a cathode ray tube. It's a glass tube. There's a gas inside of it, and there's metal plates on each side that have an electrical charge. Inside this glass tube is a gas. It's just a very small amount of gas at low pressure, but when he passed electricity through the tube, it caused the gas inside to glow. It would basically release energy as it traveled through the gas. Now, in between those two plates, he put this other insulating plate that just had a tiny opening in it. So the electricity would pass through the gas in a beam, and that beam would glow. That's the cathode ray. He then took electrically charged plates, positive and negative, and discovered that as that beam went past them, it was pulled towards the positive plate or repelled from the negative. Now, he mixed it up a little. He tried different gases, and he discovered that everything always happened the same way, no matter what gas it was. What that told him is that the gases carried the electricity through a charge. They all had the same charges in them. Those charges were negative, and he knew that because they were drawn to this positive plate, and as the electricity went through the gas, it would bend towards the positive plate. Because they all bent the same way, no matter what gas it was, that told him that every element had these particles, and they always acted the same way. At the time, he called them corpuscles, which just meant particles. We now know those as electrons. Okay. His predictions about the atoms weren't exactly the most accurate. He proposed that atoms were sort of this positive goo that had little tiny negative particles in them. These are what we now know as the electrons, the negative particles. The positive goo that surrounded them, he described being like plum pudding. You have the dried plums being the electrons, and they are suspended in this goo of positivity, which is the pudding. Okay, next scientist on the list is Robert Millikan. Robert Millikan took Thomson's experiment a little bit further. He actually found the electrical charge and the mass of the electron. And the mass of the electron is a very, very tiny number, 9.109 times 10 to the minus 31 kilograms. He discovered this by looking at the charge of the atom and comparing that to its mass. He used this tool, which is called the oil drop apparatus. This apparatus basically has very little air inside it. It has a negative plate at the bottom and a positive plate at the top. And he would pass very tiny droplets of oil into this big metal drum. Now, as the oil droplets fell, he would hit them with ionizing radiation. In other words, they would become ions. And as they fell past this positive plate, these negative oil droplets would be attracted to the plate. Now, we know all objects fall because of gravity, so the oil droplets in here are falling because of gravity. But when they pass this positive plate, they're drawn to it. By adjusting the amount of electricity going through these plates, he was able to stop the drops from falling. In other words, to counteract gravity, so that as gravity was pulling them down, the electrical charge was pulling them up. At the exact point where the drops levitate in midair, he discovered that gravity was equal to the electric charge, and he used that to discover the mass of the electrons. Our next group of experiments focus on discoveries about the atom that we made once we knew about nuclear reactions. In the late 1800s, when X-rays were discovered, scientists learned that X-rays had the ability to make certain minerals glow. And scientists were trying to find a connection between this glowing and the X-rays, and they accidentally discovered basically radiation. They discovered that radioactive substances gave up two different types of particles. For lack of a name, they called them alpha particles and beta particles. And a scientist named Ernest Rutherford was trying to figure out what these particles were. To do this, he conducted an experiment called the gold foil experiment. In the gold foil experiment, he took a very thin piece of gold foil and he wrapped a detecting screen around it, and he fired alpha particles, which come from nuclear reactions, at the gold foil. Now, the gold foil was really, really thin, very fragile, so as he's firing these high energy alpha particles, he expected the gold foil to get shredded, to be torn apart and destroyed, and that's not exactly what happened. What happened instead is the alpha particles went right through the gold foil. Most of them did. A small number of them, though, actually bounced right back, and then a small number went through but bounced off in different directions. This isn't what he expected, because the gold foil was really fragile, so he thought it would get torn apart. That didn't happen. Now, his experiments showed him that the alpha particles had a positive charge to it. So if you imagine the gold foil being a very thin layer of gold atoms, what he came up with is that every atom has a very, very tiny center that's positively charged. as these alpha particles went by that center, some of them were repelled from it because they were positive, the nucleus was positive, so they were shot off at different angles. If they got really close, the angle might be more extreme. In some cases, they hit the center of the atom and they bounced back. So what he discovered, again, center of the atom was positive. However, he also discovered that most of these particles went right through the gold foil, and that's because the atoms are mostly empty space. So as these alpha particles were flying at the gold foil, most of them went right through the empty space of the atoms, but whenever they got too close to a nucleus, they bounced back. From this, he discovered the nucleus, but he also discovered that the nucleus is extremely small. It's like much less than 1% the total size of the atom, and yet it makes up well over 99% the mass of the atom, which again tells him that the atom is mostly empty space. So what he discovered is that all atoms have a nucleus, just like so what he discovered is that all atoms have a nucleus, and put his work with J.J. Thomson's, we now know that all atoms have electrons that are negative. All atoms have a nucleus which is positive, but we don't yet know what's inside the nucleus. That would come up later, and it was actually explained by one of Rutherford's students, a man named James Chadwick. Now, back to the electrons, though, for a second. A scientist named Niels Bohr, which I'll get into more in the next video, was experimenting with hydrogen gas, and he discovered that if you put electricity through hydrogen gas, it glows a pink color. By studying the glow of hydrogen, he predicted that electrons were in specific paths around the nucleus of the atom, and they could only be found in these paths orbiting the nucleus, kind of like planets orbiting the sun. And last, back to James Chadwick. James Chadwick was Rutherford's student. He actually was the first person to discover what the nucleus was made up of. So he found out that there were positive charges in there. Those were the protons. But he also discovered much of the mass of the nucleus was made up of neutrons, which have no charge. In the next segment, we'll look at how the numbers of protons, neutrons, and electrons could be determined by looking at the periodic table and having just a little bit of information in addition to that. Thank you.